Welcome to machine learning. This is the 14th lecture on attention and transformers. Let's start with an experiment. Attention in us humans helps, processing complex information. So if you look at this image that I pulled from Google, this is a pretty cluttered scene. But since I haven't told you what your task is, you don't really know how to or what to focus on. So if I ask you now, how many yellow objects were in this image, I guess you will have a hard time. Yeah. But if I told you now focus on white objects, I think you will be able to answer questions. Okay, so how many plates were on the table? I don't even know myself. I think 2. So attention really puts a weight on some parts of the input so that the downstream task and the output can be performed better. So attention is a concept that has been taken up by the community, by the machine learning community, and has since been driving especially NLP. So for example, tasks like machine translation has strongly benefited from attention mechanisms. And today we're going to talk about mainly this example task. How can machines transform an input sentence, like for example, the agreement on the European Economic Area was signed in August 1992, to an output in a target language, for example, French. And translating from one to the other language often comes with a couple of difficulties that attention successfully addressed. For example, first of all, we don't have a one-to-one mapping of words, right? So, for example, here the could be either la or le, so the feminine or the masculine pronoun, and we only know that by looking at the subsequent word. Yeah? So, and sometimes these dependencies can span, many words. Yeah? For example, with a pronoun we mean something that has been mentioned a couple of sentences ago, and so sometimes also, here and here and here, the order of output words, of output tokens, although there would be a one-to-one mapping, is somehow changed, and attention will be beneficial, or will be useful to kind of model these problems or overcome these challenges. Yeah. Okay, machine translation is an example of like a whole family of problems called sequence-to-sequence mappings, or sequence-to-sequence problems or tasks. And you'll often find the term transduction problem, which is defined in many contexts quite differently, but here it means that we have a model that basically accomplishes 2 tasks. One is encoding the input sequence into a so-called intermediary language, and then it transmits or transduces this encoded input as this vector z here. And then the second part of the model will take this as an input and will generate the target language. So we usually, and that's like the predominant architecture in machine translation tasks, we use an encoder-decoder architecture, right? So for this part, obviously, we will encode the input x, and the decoder will decode this latent space representation of the input into the target language. And we usually generate text word by word or token by token, as we discussed in the RNN lecture. So the encoder takes in the entire sequence, the entire input sentence, passes along this vector z, and d now receives, for example, this first token beginning of sequence boss, and then will generate subsequent words or tokens that we'll then feed into the decoder that will condition the decoder to produce an output distribution of the subsequent word, okay? Until we then finally receive this end of sentence or end of sequence token that will then make us stop generating the sequence, right? So this is the way we use encoder-decoder architectures, and we'll use these here in the lecture as well. We'll start by applying this encoder-decoder concept to RNNs. So remember, and if you can't, go back to the video that we had last week. We can think of the encoder as one recurrent network that produces a hidden state after seeing each input tokens. And this hidden state then serves as this intermediary z, and will then be passed to a second RNN that will then generate the output tokens, and each output tokens, as we saw, will condition the next time steps. And so I've chosen to present very shortly this paper here, heavily cited, one of the first NLP papers that used attention. And I think it's really good to see how they applied that, because it kind of conveys the notion of mixing representations of different input tokens. That'll be used also in the second paper that I'll be presenting to you. And also, I think it's very important to see that this idea introduced with RNNs kind of led to the end of RNNs. Yeah. So in this paper, the authors use a bidirectional RNN, which is basically two RNNs that you feed with the sequence in normal order, right? So let's think of this first RNN producing hidden states F. And this first RNN sees the sequence in the normal order, but you could also reverse the sequence and feed it to a second RNN that creates hidden states B for backward. And then you can use these two hidden states as a representation of each token, let's say, having some kind of information about the bidirectional context. Okay, so we'll concatenate these two hidden states into a vector h, yeah? And hj is the jth representation, or the representation of the jth token. Now we will add these things into a vector c. This is equivalent to the z that will pass to the decoder. And this c here may look different depending on which output token we are currently generating, right? So I here is referring to the output, j is the input. So we'll always sum up all input tokens represented by h, but with a different weighting. And these alphas will be learned, okay? We'll come to this in a second. Now, this vector c is then passed up to the decoder, which is an RNN again that sees the state of the last time step and this intermediary representation of the input sequence, and then generates those outputs. Now, where do these alphas come from? There's a third, well, a fourth network, this time not a recurrent one, just a feedforward network, that is producing these weights, these alphas, yeah, and is conditioned by the hidden state of the output RNN for the last time point, and receives also the unweighted representations of the input sequence. Okay, so basically these will always stay the same, and this representation will change, and then it will produce these connection weights. Okay, so don't worry if that was too fast for you, but I wanted to point out one important thing, right? So we will pass down to the decoder a vector C that is the sum of those representations here, and by by arranging these alpha i's, or by choosing those alpha i's in such a way that some input tokens receive higher weight, even in the limit, this being 1 and all these connections being 0, you can focus, you can attend to different input tokens, input elements. Okay, so for example, if we are about to generate a word that could be a one-to-one translation, but isn't in the same index in the input sequence, we can attend to previous or later positions in the input sequence and then do this one-to-one mapping, yeah, if we wanted to do that. And the cool thing now is that presenting input-output sequences in training, we can backprop into A and produce and learn attention masks. Okay. Now this is what is shown in the results section of this paper. So you can visualize these alpha ij's in this kind of matrix, right? One dimension shows the input sequence, and the other the output sequence. So for example, if we look at zone here, each of these entries, each of these values represents the weight. The hidden state of the input is added into the CI vector. Okay, and so we'll see that zone attends to the word area, and not to the same position in the output sequence, input sequence here that would correspond to European, which kind of makes sense, and so the translation can be done with this representation of the input sequence that at this time point has or more strongly integrates the encoded token area. Okay, good. Now this should just make up your mind how attention was implemented a couple of years ago. Now this paper by people at Google is, I think, the landmark paper, the first paper that introduced the transformer idea. Since then, transformers have been, presented in different variations, but I think it all goes back to this very, very cool paper. You'll find a ton of blog posts many of which are omitting details. So look at the description. We'll list the best resources for you to read up on this topic, and of course the paper is the primary source here. Okay, as I said in the previous slide, transformers are dominating NLP. Although recurrent networks haven't died, I mean, people still use them for many different tasks, but not in this natural language processing domain. Okay, so how does this work? Again, we have encoder-decoder architecture, and the encoder now is presented like that. So we'll have an input sequence X, which could be any length. Could be one word, could be obviously many. And this encoder consists of actually 4 layers. And one is self-attention, which is the primary focus of these upcoming slides, and a couple more things that we'll also discuss later. So before we go into detail about self-attention or attention, let's talk about how the input is represented. And remember last lecture, we introduced you to one-hot encodings and character embeddings. Just think of your inputs, of your input tokens, as d-dimensional embeddings, okay? And often people use byte pair encodings, so these are subword tokens, and they are along arranged along this dimension, the first dimension. So n many, so capital N is the number of tokens in your input sequence. Okay. The first step in every transformer is mapping the input tokens in X to internal representations of these tokens. And we'll use 3 different representations that we call queries, keys, and values. And I'll show you in a moment why we need 3 and what are the purposes of these. But so they're basically just linear mappings, right? So each token in X is multiplied by a matrix W, and then therefore shortened, right? So the dimensionality I'll show you on the next slide. But so this is basically, each of these elements is multiplied, projected down to this smaller vector space of dimensionality dk. Okay, so we'll have parameters wq, wk, and wv that will be backpropped into. So these parameters decide how to represent these input tokens, and we'll see in a moment what we do with these 3 matrices. But just to get you a notion or an idea of how big these objects are in the original paper. So for example, the input dimensionality was 512. We'll have input sequence lengths like around 100, or I think the maximum was 200, although they don't say in the paper, but I remember some code saying that. Oh yeah, and the internal dimensionality of the model was 64. Modern transformers easily go beyond 2000 or 4000. Yeah. Okay. Now, the core of every transformer model is self-attention. So self-attention means the input sequence attends to itself. So each input token kind of looks at all other input tokens. And this form of attention is called dot product attention, because we will compute a dot product between the representations of each input token in Q with all representations of input tokens in K. Okay, so we have a query, or all queries, we have all keys, and we'll compute the dot product. Yeah, so we in the end have a 100 by 100 matrix, and each of these numbers here is the dot product of these 2 matrices. Yeah, or of the vectors in these two matrices. So in a way, right, dot product, you may remember in one of those first lectures that we had, is a similarity measure. Okay, so if we have found somehow encodings for our tokens that are meaningful, and remember, these will be learned because we have parameters in W, Q, V, and K. So if we learn those representations to be good, the dot product similarity will be high, right? Of similar tokens, and will be low for not so similar tokens. Okay. Now we'll push these into the softmax function, and then it'll look like this. So the output here is full of numbers, and I just visualized, one of those rows. And so softmax will operate on each of these rows, right? So the sum of all these 100 numbers will be 1. And this corresponds to an input weighting, okay? So we have two, so the same sequence twice. And so those violet connections here show the biggest attention, right? So maybe this bright bar here is the 1 in the otherwise 0 vector, and this will correspond to which input token attends to which other input token. This brown encoding here is something else. I'll come to this a couple of slides later. So, but how do we use this attention mask? So, right, we have many of these rows here. So all of those input words or tokens attend to all other input tokens, and so you can imagine this as like a graph. Which I just showed you here. I cropped this figure from the paper. So the next step is now we'll use this attention mask to mix the values. And again, the matrix V is some representation of the input sequence of the input tokens. And by multiplying this attention mask with this matrix V, we'll get an output representation of our input sequence. Yeah. So what happens is this. Just look at the first output value here. This is basically the dot product of these two vectors, which is, remember, this vector has sum 1, which is just a weighted sum, right? A mixing of the first elements of all these vectors. Okay, so, and then the next position is again a weighted sum of all of these second elements determined by this mixture vector, let's say. Okay, so in the simplest case, we have like a one-hot or one-hot vector here, which would then just be or result in the permutation of the values. Okay. Okay. So the encoder, the encoder's first component is the self-attention layer, which is, given Q, K, and V, linear projections of each of these elements in the input, can be visualized as this computational graph here. Very simple. Now, to make it a little more complex, the authors introduced so-called multi-head attention. And this means that we not just do this self-attention once, we'll do it many times. So I think in the paper was 8 8 times, right? So the input is projected 8 different times and in 8 different ways with 8 different weight matrices to Q, K, and V for the different attention, heads, right? And these outputs, these heads, are then combined in such a way that we first concatenate each of these heads. These may and will look different. So the same color coding here doesn't mean that the values are the same. Obviously, they should just refer to the index of the items, of the tokens. And then we'll multiply this by W, which kind of mixes, whatever it wants into the output. And again, WO for output is a learnable set of parameters. Now, remember we had DK as I think chosen as 64. So this is the internal attention dimension of both Q and K, and also V was chosen to be 64 dimensional. So each of these outputs is 64 dimensional, and we'll project this to an output dimension of 512. And that was exactly what we used as an input, right? Now, the next step is this. So we have our input X, and we'll use the skip connection here that the resonant architecture introduced first. And we added on top of the output of this multi-head attention, and then normalize. And we'll use so-called layer norm. So I put a link here, and we'll also put it in the description, which is like a learnable kind of normalization, right? So pretty similar to batch norm. I think we had this in one of the earlier lectures. Layer norm is also kind of normalization. The next missing, or the last missing part, is a simple feedforward network. So each input tokens, yeah. So we are here in 512 dimensional space, is then mapped to a hidden layer, right, with this matrix W1 with additional bias, and then pushed through a ReLU. And more modern architectures use GLU or other activations, but this original paper used ReLU. And then these hidden activations are then mapped back to the model dimension, so 512. And then pushed again through add norm, and we have this skip connection here as well. And that is the output of the encoder. Now the authors use six of these encoders stacked on top of each other, and then the final output is then passed to the decoder, and we'll come to this in a second. But let me just summarize what the attention mechanism is really doing in the encoder. So remember we had our matrix Q, which is a 64-dimensional representation of each of these input tokens, and we'll multiply this with another set of input token representations learned, with this matrix WK into this matrix K, and so we'll multiply this, and this will produce an attention map and kind of a mixing matrix, let's say, for the values, which is the third representation of input tokens. Okay, and this mixing then creates the output of the attention, which in the multi-headed attention kind of way is concatenated and projected to the output dimensionality of 512. And this is done a couple of times, 6 or 4 or so. Okay, so I can understand when you think, well, what, this is pretty arbitrary, and why does this even work, and what does this even mean? So think of the encoder's task, and by the way, the important parameters here are those projection matrices WQ, WK, WV. So the encoder needs to find a representation for the input tokens in such a way that they create a good attention mask. Yeah. So this also means that, for example, these dot products here have to be high when the meaning of those words, of those tokens, is similar. And those values, these are the representations that we kind of mix because, following this attention mixing matrix here. These values have to be optimized for, for the decoding. So the encoder's task is to come up with this intermediary language Z, right? Remember that we pass to the decoder, and all these parameters here are optimized for this meaning. And well, we do have a couple of more parameters, right? So the multi-head concatenation projection to the 512. And also here the two layers in the feedforward network. Those are parameters that will be learned, but I think those are the most important ones. And it will become clearer when we think about how we use the decoder in inference. But this as like a visual summary of the encoder. But now let's have a look at the decoder. The decoder now looks a little different. It also comes with n, times. N here is 6, I think, in the paper, and comes with 2 multi-headed attention layers. One of which looks a little different, and we'll talk about that. But the rest really looks the same. We have skip connections and add the results together and normalize, and we have also the feedforward network with the ReLU nonlinearities, and then of course at the end of the network, at the end of the decoder, we create a softmax distribution over the next token to put out. No? We'll not yet talk about what these things mean, but we'll come to this in a second. Okay, so let's review real quick what those differences are of these 3 different attention layers. So the first one is, like discussed, the encoder attention layer, which is a self-attention layer, right? So those inputs are query, keys, and values drawn from the input. So input elements can attend to each other. So this is self-attention. And the same self-attention mechanism is applied in this first part of the decoder. Here, the output sequence can, or items or tokens in the output sequence can attend to each other. A little differently is this third part. This attention layer receives values and keys from the encoder. So this is where the input sequence has been encoded into. But the queries are for the output, right? So we'll now relate output tokens to input tokens, okay? So this is therefore no self-attention. It's called encoder-decoder attention. Now, let's have a look at the second part here. So why does it look differently? Why does it say masked multi-head attention? And then we'll later come to this part here. Okay, so let's first imagine how the decoder will be operating in inference mode. So we'll put in our boss token, our beginning of sequence token. And so the decoder will receive this one token, and then we'll be generating the next output, actually the first word of the sentence, and then we'll have this word and the boss token, so 2 tokens as input, and we'll generate the third, and so on. So in this operation, the self-attention in the first layer, in the first attention layer, will not be able to look ahead. Yeah, so there will be no future words that we can draw information from. But in training, we have our entire sequence already, right? So we have, our given English sentence and the given French sentence, and we'll shift this right, put in the first spot the boss token, and so this will be pushed through the entire decoder. And now the attention layer will be attending all of these tokens input to the decoder to all other of these tokens, and there will be attentions being computed that won't be there in inference. And now, since we want to train those matrices WK, WQ, what is missing, V, to find token representations that kind of make sense also for inference, we need to mask out these future words. Yeah. So, for example, we have an English output. Let's say, "How are you?" and "How are you?" are or each of these tokens are compared, and this is our attention mask. And now we'll see that those values here. So let's see this top right value is larger than 0. This means that then multiplying this to the V matrix will also use future words to come up with a representation for how. And that is something that we don't want. We want to set these values, so above the diagonal, to -infinity, so that then applying softmax will give us 0 probability for these attention values. Okay, so let's have a look at this last attention layer here. So in the encoder-decoder attention, again, we'll take the values and the keys representing the input sequence and the queries from the decoder, and do the attention mechanism. Now, I think it's very important to take your time to understand what's going on here. So again, go back to how we want to operate this decoder. So this message coming from the encoder is kind of telling the decoder, okay, that is what you should be translating. And Q is representing what we have already been saying, right? So this is the sequence up to now. And the task for the whole network is to now predict a distribution over output tokens. So we kind of condition the network to what it already has said. And now, of course, this attention layer here will be able to use what we have said in Q and attend to all other words that we have in our input sequence, and define, the mixture for the output representation for the higher layers. So those inputs then determine, in the end, the output distribution. So this needs this needs to work with different sequence lengths. And I think a very important aspect and a very cool property of transformers is that it does, not just because, you know, input and output, so English and French sentences are differently sized or different in length. It's because the attention mechanism, so the matrix multiplications, are designed in such a way that the sizes match, even if we start with one output token. So let's do this here in an example. So in inference, we will start with one token, the boss token, right? So this means network, tell me the first word, okay? Conditioned on what was our input sequence. And so in this attention layer here, we'll use just one token. Yeah, so that is the representation of the boss token. And this will be, you know, increasing in size, you know, the more we have generated. But let's just, you know, for the fun of it, see how these multiplications pan out. So the representation of the first token is then multiplied. So we're taking dot products, remember? So similarity measures with each of these keys. So each input tokens coming from the encoder. And this will produce just a vector, so a softmax distribution that we'll then multiply with the values also coming from the encoder. So those words, those meanings are available from the input. And now we'll create a representation for the decoder state, let's say, by merging these together given this attention mask. And this will be A. So the output of this one attention layer. And so, right, so this will be passed up, and this can be done 6 times or so, right? So I think the paper says n is 6. And it works. And now think of the sequence being 2 tokens long or 3 tokens long. So let's say it's 2. So we'll have, you know, after this multiplication, we have 2 of these softmax distributions. And then we'll multiply these and we have 2 output tokens, right? And so this way, the decoder can use a variable number of tokens to learn this function of producing the output distribution for the next token. Now the problem is that the model has no information about where each token is. Yeah, so this token is just each of these Qs and values and keys are token representations, you know, that are independent of their position, right? So I don't know, think of a word, like, I don't know, mobile phone or whatever, screen, computer, and these words or these tokens will be represented in a space, you know, independently of where they are in a sentence, because right now we haven't yet told the network, told the model where these words were, right? And these representations don't know how to integrate this kind of information. Yeah? Implicitly, yes, there is some sequence information in here, but the representations don't know nothing about it. And it turns out that it's very important to have this kind of information for the model to learn anything meaningful. Yeah. So also those feedforward networks in the encoder and also in the decoder, they're just touching single elements, single tokens, right? So they map single tokens to single tokens. So we need a way to integrate this positional information in order for the network to learn something meaningful. So what you could do in order to make your tokens kind of know where they are, for example, you could add an additional dimension which takes values between 0 and 1, right? So for 0, the token is at the beginning of the sentence, and 1, it's at the end. Now, this may work a little bit, but there are a couple of problems with this. So, for example, if you have very short and very long sequences, these numbers, won't be able to represent an absolute kind of position. Will only be relative to the sequence length, which again is something that the model doesn't know. And also, this representation of position doesn't really generalize, or the model with this representation of position won't be able to generalize well to sequence lengths that it hasn't seen yet. Yeah? And so the authors in this paper proposed this positional encoding with sine and cosine waves, which is such a great idea. So I think it's an underrated contribution, and I hope you feel the same after seeing what I've now explained to you. So the positional encoding is a function that depends on the token's position, obviously. So, for example, here we have 100 different possible positions. So these are integer values, obviously. And so what it is a 512 dimensional vector that is composed of sine and cosine waves in alternating fashion. So you always have a pair of sine and cosines with a given frequency. So let's say we are in the first two components of this 512 dimensional vector, then progressing through the input sequence, going from 0 to 100, for example, these sine waves will, just like here, will be, for example, this blue and this yellow or orange line. Yeah, so will be values between 1 and -1. And the third and fourth position now use a different frequency of these sine waves. So, for example, the green and the red curve here are the next positions. Yeah. So this I here is really the index of each of these pairs, and as you can see, so this constant here is exponentially made bigger. So any sequence position going from 1 to whatever will reach 2 pi after more steps, right? So this means it needs longer, so the frequency is higher for higher i's. So how does this work? Well, so we have our original output and input embeddings, and we'll use the positional encoding now to add this on top of these vectors, right? So remember, we had 512 dimensional tokens, and so our positional encodings as well share the same dimensionality, and we'll add them. We could be concatenating, but this will increase the model size. And it turns out that it works if you add these onto each other just as well. Yeah. So by doing that, our tokens now come with a position, right? So the token car at the beginning of a sentence will be numerically different from the same token at the end of the sequence. And so now tokens live on this manifold, right? So adding vectors on top of this kind of nice high-dimensional function comes with, or enables the mappings, those linear mappings WQ, WK, and WV to kind of take this manifold into account, right? And and this comes with two properties that are nice. First of all, mapping to Q and K, so those vectors that we'll then multiply together, so that these representations are multiplied in a dot product. If tokens are close in the sequence, the positional embedding will be close. Yeah, and so if those matrices W, Q, K, and V don't do anything and just learn the identity, the dot product will be high. Yeah, so the positional encoding implicitly kind of creates this local attention. Then the other cool thing is that the positional encoding, so this 512 dimensional vector at a certain position in the sequence, can be taken and mapped linearly to any future or past position. So linearly means just by multiplying a matrix, and that's something that our matrices here can learn as well, right? So the model may be generalized much better to unknown sequence lengths and dependency lengths and so on. By the way, some people have asked me, so those positional encodings, if you push them through this large stack, don't those encodings kind of vanish in the end, or like be like, or are faded out or something? No, they won't, because we have those skip connections. Okay, so even in the highest layer, they're fresh, yeah, as just produced here. Okay, let's summarize. So transformers are a very cool sequence-to-sequence architecture with an encoder stack and a decoder stack. The inputs are first processed, pushed through these different layers that we've discussed, and produce a latent encoding that kind of represents the input, but also comes, with a positional encoding for each of those tokens. Now, in training, the encoder receives the sequence as an input, and the decoder gets the same, so the target sequence shifted by 1. And so we learn all those parameters through this architecture, right? With many of these training examples. During inference, though, the encoder delivers the same encoding for the sequence, for the input sequence, but the decoder now produces a growing sequence. Okay, please note this difference. And the transformer architecture allows that, which is a very neat point. Transformers are faster than recurrent models if the sequence length is smaller than the dimensionality of the model, which is so in most cases. And transformers can be parallelized much better than recurrent networks. So transformers were and are the dominant type of model have become the dominant type of model in the last couple of years. And maybe one last slide. This is a paper that is, I think, still under review by people at Google. Again, some of those people were also on the Attention's All Neat paper. I think it's interesting to see that you can apply transformers, so this multi-headed attention, to pixel sequences, and come up then with a model for image classification, for example, that is as performant or maybe even better than current convolutional architectures. So there's no convolutional layer in here. This is purely attention based, and this works. Though one thing to note here is that it seems that the inductive bias that convolution kind of introduces to the model helps in training very performant models with less data. So these vision transformers need huge amounts of data. So the authors, I think, wrote only 14 million samples, so that's ImageNet, isn't enough here to become better than the baselines. And then they used, so the biggest data set was 300 million images. So that's something that we can't do at home. But so the transformer in the original version that I've just shown you can be trained on our machines these days. And that's what you have to do for your assignment. That was it for today. Thanks for watching. Leave a comment. See you on Monday. Bye.